I'm talking about sequences, and what we're going to do today is get a little more specific and just deal with arithmetic sequences. And an arithmetic sequence is a sequence if you're adding the same thing to each consecutive term. So, for example, if you have the sequence a sub 1, a sub 2, a sub 3, and if you take any term and subtract the preceding term, and you get the same thing, so like the second term minus the first, or the third term minus the second, and so on, and you get the same number, then that is an arithmetic sequence. And that number that you're adding or subtracting each time is called the common difference. So they still call it a common difference even though you might be adding the same thing each time. So it works either way. So, and the letter they use to represent that is the D. So these are arithmetic sequences. So let's take a look at some examples. So if I tell you the nth term is 4n plus 3, so basically that's a formula for telling you what the value of the nth term is. So the fourth term, or the seventh term, or the eighth term. And if we're looking for the value of the eighth term, that means the n is 8. So in the formula then, we would plug in the 8 for the n. So 4 times 8 plus 3. So 4 times 8 is 32, plus 3 is 35. So the eighth term in this sequence is 35. If I want the third term, okay, so the value of the third term, the 3 then is the n. So into the formula, I'd plug a 3 in for the n. So 4 times 3 is 12, plus 3 is 15. Okay, so this is an example of an arithmetic sequence. And if you just take a look here, from 7 to 11, you are adding 4. And from 11 to 15, that's a jump of 4. So this is arithmetic because our common difference is 4. Okay, on the next one, it says the nth term is 7 minus 5n. So let's just say we want to find the fourth term. So that means the n is 4. So we plug a 4 into our formula. So 7 minus 5 times 4. 7 minus 20 is negative 13. And sure enough, our fourth term is negative 13. And if we look at the difference here, so we're going from 2 to negative 3, so that means we're dropping 5. Negative 3 to negative 8, we're dropping 5. Or you can think of it as we take any term, so let's take the fourth term, 13, and subtract the preceding term. So that means we would add 8. So our common difference is negative 5. In the next one, the nth term is 1/4 of n plus 3. So let's say we want to find the second term. So that means our n is 2. So we would plug a 2 into our formula to find the value of that second term. So we need 1/4 times 2 plus 3. 1/4 of 5 is 5/4. Okay, so let's figure out what our common difference is here. So to get the common difference, remember we can take any term. So let's take the second one minus the first one. Well, 5/4 is 1 and 1/4. And if you subtract off 1, you get 1/4. So we're jumping here a positive 1/4. Let's try it with the second term, or the third and the second. So let's take the third term, 3/2, and subtract off the value of the second term. Okay, so to subtract, we would need a common denominator. So we would change the 3/2 to 6/4, and 6/4 minus 5/4 is 1/4. So here we're making a jump of 1/4 also. So that is arithmetic because we constantly add 1/4. We're not multiplying by a fourth, but we're adding a fourth. Okay? Take a look at this sequence. First of all, is it arithmetic? So we'd look at it and we'd say, well, the difference between the second and the first term is 3. The third and the second is 3. The fourth and the third is 3. So yes, indeed, each time we are adding 3. And I should have that one. We're working with infinite sequences, so they're ones that keep going on forever. But yes, it is arithmetic, and our difference is 3. So when you see a sub 1, that means what's the value of the first term. So the first term is 5. A sub 2 means what is the value of the second term. That would be 8. A sub 4 would be 14. So we want to know a sub n, so that means we have to figure out a formula. Well, remember that we are going up by 3 each time. So I'm going to set up a little table then, and so this is going to represent n, and this is going to represent the nth term. So for example, if n is 1, the value of the first term is 5. If n is 2, the value of the second term is 8. And if n is 3, the value of the third term is 11. Well, so that's good enough to help us find a formula. So if we're growing by 3, when here we're growing by 1, our rate of change is 3/1. So remember, we refer to it as the slope for a linear function. So a linear function is one that has a constant growth rate. So like if rise over run is 2/1, that means for every one we go over, we're going up 2. Well, that's exactly what's going on here, only for every one we go over, we're going up 3. All right, so we know that if we were to write the linear equation, we know that we'd have y is equal to 3x plus, and then we have to figure out what this number is we add on. Well, that represents our y-intercept, and so our y-intercept, if we continue the table on backwards, so if I go from 3 to 2 to 1 to 0, I'm dropping 3 each time. So if at 1 we're at 5, when I drop 3 back, I'm at 2. So I would get the y-intercept to be 2. Now instead of using an x and a y, we're using an n for an x. So if I put in an n, I want to take 3 times n plus 2. So let's see if that works then. So we're saying the value of the second term, we would use our formula, 3n plus 2, but we want the second term, so that means we want the n to be 2. So 3 times 2 plus 2 is 8. And yes, our second term is 8. Okay, let's try the fifth term. So if we're looking for the value of the fifth term, that means we want the n to be 5. So 3 times 5 plus 2 is 17. And yes, indeed. So that looks like we got the right formula. So 3n plus 2. So keep in mind then, an arithmetic sequence may be thought of as a linear function whose domain is a set of natural numbers. So we're just using natural numbers like 1, 2, 3, 4, 5, not 1 and 1.1 and 1 1/2 and 1 3/4. So just a domain of natural numbers makes sense in a function or in a sequence. All right, so I've got a formula for you here that says the value of the nth term, so the a sub n, is equal to d. Remember, d stands for the difference. And the n is going to stay in there. So the n stays there. So we'd have to fill it in with the difference and then the c, what this number is here. And remember, if we refer back to it and we look at like how we write a linear function, the m then is our difference, and the y-intercept is this c value here. Okay, so remember, the y-intercept is not the first term of the sequence. The first term is what's the value when the x is 1, so the y-intercept is when x is 0, or in our case when n is 0. So the y-intercept is not the first term. That's kind of confusing sometimes to kids. Okay, so that means the y-intercept, or the c, is whatever the first term is minus the difference. Okay, well, let's think of our last example that we had. And we had the sequence 5, 8, 11, 14, 17, and so on. So we were taking a look at this sequence. So I'm going to take a look at all of these formulas in relationship to that last sequence that we were talking about. So let's go back up to this one that says the a sub nth, or the nth term, is equal to the difference times n plus c. Okay, so our difference. So we look at our sequence and we see that we're growing by a positive 3. So our d is 3. And then the c, we said, is similar to our y-intercept if this is a linear function. So the c is not 5. It's not this value here. The c then is the first term minus the difference. All right, well, let's take a look at that. In our sequence, our first term is 5. So I want to go 1 before that. So that means I would, instead of add on the difference, because we're going backwards, we're subtracting on the difference. So we get a c value of 2. So for this formula then, for the a sub nth, we would get our difference of 3 times n plus 2. And let's check it again. So let's say we want to find the value of the third term. So that means our n is 3. So we'd go 3 times 3 plus 2. 9 plus 2 is 11. That should be the value of our third term. And yes, it is. Okay. Another way to get the value of the nth term is simply to take our formula that we had up here and replace the c with what it's equal to. So there we're using our substitution property again. So notice from the a sub n formula up here, I have d times n, but in place of c, we put a sub 1 minus d. So if I rearrange this formula then, and I notice that 2 of the terms have a d in it, so I'm going to switch the order of the a sub 1 and the dn. So I'm going to put the a sub 1 first, and then I'm going to put d times n, and then minus d. Now these two have a common factor. Their common factor is d. So I'm going to factor out that d, and I get n minus 1. So here is an alternative formula. And normally you'll see it written with the n minus 1 and the d switched around. Okay, and that's the way I learned it, so I'm probably always going to write it that way. So here is an alternative formula for finding the value of the nth term. And if you know what the y-intercept is, you can use this formula here. If not, you can use that formula. Okay, so let's take a look at this. We want to find a formula for the nth term, and we know it's an arithmetic sequence, so it's important to know that, whose common difference is 3 and whose first term is 2. Okay, well, let's just write out that sequence. First of all, a few of the first terms. So the first term is 2. Oh, gosh, I hate it when I do that. Come on, bring it over. Okay, now I'll get a pen to write with. Okay, so the first term is 2. Our difference is 3. So if we'd add 3 to that, we'd get 5. Add 3 again, and again, and again. And we can keep going on because it's infinite. We'll stop there though. We want to find a formula for the nth term. Well, if I go back and I grab the formula that we just came up with, that says you take the first term plus the number of term minus 1 times d. So when we write a formula for the nth term, we keep the n in there. So we have to replace the a sub 1 and the d with numbers, but the n stays in there. So the a sub 1 stands for the value of the first term, that is 2. The difference is what I'm adding each time, and the difference was given to us, so the difference is 3. So I'm replacing the d with 3, and then we simplify by distributing the 3, and then we'll rewrite it, combining the 2 and the negative 3. So here's our formula. Okay, let's check it out. So if this is true, then the value of the fifth term we would get by replacing the n with 5. So 3 times 5 minus 1 is 14. And let's go back up here and look. There's the fifth term, and the value is 14. So here is our formula then that we were looking for. The formula for the nth term. Okay, so let's go to this one. Let me see if I can get rid of that. Can I just delete that out of there? Because that's annoying. There we go. Okay, so now the fourth term of an arithmetic sequence is 20, and the 13th is 65. So let's draw this out. So I don't know the first term, second, third, but the fourth is 20. And then fifth, 6, 7, 8, 9, 10, 11, 12, and then the 13th is 65. Okay? We want to write the first 6 terms of this. So in order to do that, when you agree, we would have to know what the difference is so that we can work forwards or backwards. Okay? So we know the value, let's write it like this then, a sub 4 is 20, And we also know a sub 13 is 65. Okay. Well, would you also agree that we could kind of ignore those first three terms and just say, well, how about we make this our sequence? Because in our formula for finding the nth term, we have a sub 1 is plus n minus 1 times d. Well, I can tell you the value of the fourth term is 20 or the 13th is 65, but I don't know either one of those. I don't know what the a value is, the first term, or what the difference is. Okay, so you could write up a system of equations, and we just did that not too long ago. So one way to solve this is saying, well, I know the fourth term is 20. So the value of the fourth term is 20, so I put in a 20 here when the n is 4. I also know the value of the 13th term is 65 when the n is 13. Okay, so our first equation then, 4 minus 1 is 3. So I have a sub 1 plus 3d is equal to 20. And then in the second equation, in this one, we would have a sub 1 plus 12d is equal to 65. Okay, so we could solve that system of equations, and then we'd know what the value of the first term is and the value of d, what the difference is. And then we could figure out anything else we need to know. All right, so because I see them lined up here, I'm just going to use linear elimination. And so I'm going to change all the values of the second one, and then I'm going to combine those so that the a sub 1 eliminate. So 3d minus 12d is negative 9d. 20 minus 65 is negative 45. So our difference is 5. All right, if our difference is 5, let's substitute it back into here. A sub 1 plus 3 times 5 is equal to 20. So our first term is also 5. So if I fill that in then, I see the first term is 5, and I'm adding 5. So the next term would be 10, 15, 20, 25, 30. So there would be the first 6 terms of the sequence. Okay? Find the 9th term of the arithmetic sequence that begins with 2, 9. All right, so sequence begins with a 2 and then a 9. And because I know it's arithmetic, we can figure out what the d is. So the d is any term minus the preceding term. So the difference is 7. So to get the third term, I would add on 7 to the 9. And add on 7 again. Okay. The 9th term, though, I am getting too lazy to keep adding on 7. So I'm going to use my formula. I want the 9th term. So I need to know the first term plus n minus 1 times d. So the first term is 2. The difference is 7. And we'll distribute. Combine like terms. And I get 7n minus 5. Okay. So find the value of the 9th term then. So I would go That means I want to put in a 9 for n. So, whoops, why did I put a 4 there? 7 times 9 is 63 minus 5 is 58. Okay, another way to do that one is just continue. Let's say that you didn't get lazy. So we're at the first, second, third, fourth, fifth, sixth. So we need 7, 8, 9. So that would be the ninth term. So from 37, we're going to keep adding on. So we'd get 44, and then 51, and then 58. So either way, we get the same thing. All right, now this one is a little bit different. This doesn't say find the value of the ninth term. This one says find the sum of the first 5 natural numbers. Well, the natural numbers start at 1, so we want to know what is the sum. What do we get when we add 1 plus 2 and so on, all the way up to 9. Well, this isn't too many numbers, and we have a calculator, so you could just punch it in and come up with that easy enough. But there was this mathematician, Carl Friedrich Gauss, who was asked to do this in school, and he came up, he had to do like, I think, the sum of the first 100 numbers, and it didn't take him very long at all to come up with that sum, and this is what he did. He took that sum again and rewrote it, starting with the largest. And I'm sure he didn't write all of them out because he saw the pattern fairly quickly. Okay, so if I just write them in the reverse order and I take a look at each of the individual sums, like the sum of these two, so the highest plus the lowest, in this particular case, I get a 10. When I add these, I get a 10. And here, I get a 10, and so on all the way down. So when you add those together, you end up with 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 factors of 10. So when you add those together, does that make sense? You're going to get 90 because you get a 10 here and you get a 10 here, and there are 9 of those. And then on the other side, when we add s plus s, and the s represents the sum of the left side of the equation, we get 2 times the sum. Keep in mind where that 10 came from. We got the 10 by adding the highest and the lowest and the second highest and the second lowest numbers together. But would you agree that that 10 is going to be representative of the first term of your sequence and the last term of your sequence? So the first term plus the value of the last term. But I don't want what the double the sum is. I just want to know what the sum is. So that means I have to solve this equation for 2. So the sum is equal to, in our particular case, it's going to be 9 times the first number in the sequence was 1. The last number in the sequence was 9. So 9 times 10 divided by 2 is 90 divided by 2, or 45. But what we're interested in is this formula that Carl kind of created on his own when he was back in school that says to get the sum, you would take 9, which represents how many numbers you're adding together, times the value of the first term plus the last term divided by 2. So that's a formula that we can now use because of what he was able to come up with. So let's use that formula to find the sum of this finite arithmetic sequence. So I want to find the sum of these numbers. All right, so the formula was take the number of terms that you have, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 numbers in that sequence. Multiply it by the value of the first term, which is 1, plus the value of the last term, which is 19, and divide it by 2. So 10 times 20 divided by 2. 10 times 20 is 200. Divided by 2 is 100. Another way to simplify that one is to take the 2 into only one of the two. So let's say I'm back here, and the numbers that I had, 10 and 20, were fairly easy to multiply together. But let's say I'm going to take the 2 into the 20 and get it 10, and then I can go 10 times 10. So remember, you don't divide the 2 into both of them if they're factors, just into one of them. All right? Let's use that formula again then. We want to find the sum of the integers from 1 to 100. Well, if we're adding the integers from 1 to 100, how many numbers are there in that sequence? Well, there would be 100 of them. So the formula for the sum is 100 times the value of the first term is going to be 1. The last term is 100. And then we want to divide that by 2. So we have 100. 1 plus 100 is 101. So now on this one, I'm going to divide by the 2 first of all. So I'm going to take the 2 into the 100, since that's even. And that means I do not take it into the 101. So now we need 50 times 101. That should give us 5,050. Okay, so that would be the sum of the first 100 integers. Now the next one says, what would be the sum of the integers 1 to n? Okay, so for n then, we need to know, well, how many integers is that going to be? Well, that's going to be n integers. The value of the first term is 1. The value of the last term is n. And then we divide it by 2. So we can put it in another form. We can just think of it as n over 2 times n plus 1. Okay, so that is the formula for the sum of integers 1 to n. So you could replace the n with a 5, or an 11, or a 37, or a 2008, and plug in the 2008 or the 37 for the n, and there you have your formula. Now, if we have an infinite arithmetic sequence, so it goes on and on and on, well, we can't possibly find the sum of the whole thing because it keeps getting larger and larger, so the sum is approaching infinity, but we can find the sum of the first so many terms, like the first 10 or the first 5 or the first 150. So that is known as a partial sum, because once again the sequence is going on forever and it's not possible to find that sum if the sequence is getting larger, like if you're adding 2 or 7 or 8.3 each time. So we can only find a partial sum. So what we want to do first of all then, if it says find the sum of the sequence, you better make sure that it's arithmetic, because it doesn't tell us it's arithmetic. So we're going to check that out first of all. So we look at this, from 5 to 16 is a gain of 11. 16 to 27 is another gain of 11. So sure enough, we're adding 11 each time. So this is arithmetic, and our difference is 11. Okay, so if we bring out our sum formula again, the sum formula says take n divided by 2 times the quantity of the value of the first term times the value of the last one. All right, well, we want to add 150 terms. So our n is 150. So in the formula then, we can put in the 150 here. We know because we have the first end of the sequence that the value of the first term is 5. So in for a sub 1, we can plug in a 5. But now it's asking for the value of the nth term. Well, our n was 150. So that means I have to know what is the value of that 150th term. Well, I don't know what it is, and I certainly don't want to add 11 150 times to figure it out. So that means then I go back and I am going to use the formula for finding the value of the 150th term. And remember, our formula was you take the first term plus n minus 1 times the difference. All right, so my n is 150. The value of the first term is 5. In for the n then, I put 150. And do I know the difference? Yes, I do. The difference is 11. So 5, 150 minus 1 is 149. I want to take that times 11. And if you multiply that out, I came up with 1,639. So that means the value of the 150th term is 1,644. That's not my sum, that's just the last term in this sequence. So I'm going to use that in my sum formula. So now I add the 1,644 in here. And I'm almost there in finding the sum. I'm going to take the 150 and divide it by 2. So that gives us 75. Then I'm going to add the 5 and the 1644. So I get 1649. And then if you find that product, you can verify. I came up with 123,675. That is indeed a much easier way than adding 11 150 times. Okay, so there is our formula for sum. So you've got two formulas that you need to hold on to. You have the value of the nth term, and you have the sum formula. These only work for arithmetic sequences. They are not going to work for any other type of sequence. Okay, so now is your turn. Now here are the problems I would like you to do before you come back to class. Okay, see if those formulas and stuff are enough, and if you can't figure one out, please go back and see if you can figure it out. And if that still doesn't work, then you can ask me in class. All right, good luck with those.